Hi everyone, welcome back. You're watching the 8th lecture of EE635 Applied Linear Algebra. This happens to be the second module. So in the first module, we the looked at the matrix representation of linear maps between two finite dimensional vector spaces, right? We had a callback to this idea of coordinate representation, that is given a finite dimensional vector space and uh, an ordered basis for that finite dimensional vector space, how vectors in that vector space can be represented uniquely by a column vector, yeah, with the help of this coordinate, with the help of this ordered basis, which we call the coordinate, right? And then we said that this identification of every vector with an n tuple, that's a column vector, through this idea of coordinates, is an isomorphism, in fact. That is, it's a linear map, first of all, between these two vector spaces, that is V and F to the n, where n is the dimension of V. And uh, this is also bijective, that is one-to-one and on-to. With the help of that, we found out that now if I have a linear map between, say, a vector space V and a vector space W, where V is identified with F to the n and W is identified with F to the m, right? Then, where m is the dimension of W, then the linear map phi between V and W will also have a matrix representation, yeah, that takes n tuples from F to the n and maps it to m tuples in F to the m, which represents the action of this linear map phi with these coordinates. Yeah, ultimately the equation that that tells us, that uniquely characterizes uh, this linear map as a matrix is this one. Yeah, where this BW happens to be this BW happens to be an ordered basis for W, and BV happens to be an ordered basis for the domain V. Now we obtain this matrix representation by some sophisticated argument, using the fact that this identification of vectors with columns of numbers or n tuples of numbers or m tuples of numbers, this identification is an isomorphism. Using that idea, we did this. In fact, so to recall what we did, so suppose V and W are vector spaces over the same field F, dimension of V is n, which is finite, dimension of W is m, which is also finite, BV, which is an ordered basis for V, as a vector space over F, and PW is an ordered basis for W as a vector space over F. Okay, and then so in this situation, okay, further we have phi, which is a linear map from V to W. We did this commutative diagram in the last module. So we have V, we have W, and of course we have this map phi. There is this identification, that is an isomorphism between V and F to the n, and W and F to the m. We want to get this map. So what we do is we do this by this identification. So suppose I have an arbitrary n tuple here, say alpha 1 up to alpha n. Yeah, this should go to A alpha 1 up to alpha n. If this A has to represent this linear map phi, what does this have to do? So this alpha vector must be identified uniquely with a vector here V. Use phi to come to phi V, and then use this representation. So what was this representation? this representation is via this map, and this representation is via this map. So the equation that they have to follow ultimately from this commutative diagram is that A, when acts on V's representation, must produce phi V's representation. That was the idea. And how did we get that A? In fact, using that isomorphism idea, we found out that this, if I do this diagram chasing, if I follow this commutative diagram, I get that A must satisfy, that A E1 must be phi V1, that is the first basis vector, in BV, its representation in W. This is nothing but the first column of A, because when A multiplies this E1, is a standard basis vector, it takes out the first basis, it takes out the first column of A. Second column of A E2 must be phi V2, the second basis vector's representation in terms of this basis BW. This is the second basis vector in BV. Okay, and so on till you get AEN, which happens to be phi VN, which is the nth basis vector in BV, its representation in BW. That's how you get the columns of A, right? So this is the formula for A. But as I said, this was done using a rather sophisticated abstract way of viewing vector spaces and their coordinates. What we'll do in this module is we'll demystify this idea and we'll explain this idea in a much more direct manner. Yeah, although this direct manner, because because of the very reason that it's direct, it's going to be a little more complicated, a little lengthy. Whereas this other idea is much more sophisticated, and therefore it's also kind of simpler, right? So the idea is that using this direct method that we're going to explore now, you have to understand this. But then once you get used to these ideas, you should go back to the first much simpler but sophisticated and abstract idea. Okay, so let's do that. So more direct way. Okay, so before we start, uh, we first make note of something. Okay, what is that? So suppose, so recall we have V, we have W. There's a map, linear map from linear map phi from V to W. Okay, V has a basis V1 up to Vn. It's an ordered basis. W has an ordered basis W1 up to Wn. So the V's basis we call it BV, and W's basis we call it BW. Okay. Now with that in mind, suppose phi acting on the first basis vector, its representation in BW, suppose happens to be A11, A21, up to AM1. This column size M. This is a typical vector in Fm. Yeah. What does this mean? We know that from the definition of coordinates, this actually is equivalent to saying phi acting on V1 is A11 V1 plus A21 V2 plus up to AM1 VM. Yeah, that's the unique linear combination. Similarly, suppose phi is action on V2, whose representation in W is A12, A22, up to AM2, this column vector. What does this mean? As like before, this is equivalent to saying phi acting on V2 is nothing but, yeah, phi acting on V2 is nothing but A12 V1 plus A22 V2 plus dot 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 A M2 VM. Oh, sorry. Made a terrible mistake. These vectors are, sorry, my bad. This is W1, W2, Wm. These vectors are in W, right? So W1, W1, W2, Wm. Sorry, my bad. Likewise, continue like this. We get phi acting on Vn, Bw. Suppose this is given by A1n, A2n, up to Amn, typical vector in Fm. This is equivalent to saying phi acting on Vn, the linear combination A1n W1 plus A2n W2 plus dot 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 up to Amn Wm. That's it. Okay, so keep this in mind. Now let V in V be arbitrary. Now since V1 up to Vn, which is our BV, is a basis for V, there exists unique alpha 1, alpha 2, dot 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 alpha n in F such that V is equal to, notice, alpha 1 V1 plus alpha 2 V2 plus dot 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 up to alpha n Vn. Yeah, obviously. This would then imply phi acting on V must be by linearity alpha 1 phi V1 plus alpha 2 phi V2 plus dot 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 alpha n phi V, and that's it. What we're going to do now is express these things in terms of the basis of W. These are vectors in W, right? What would they be then? They would be alpha 1 multiplying phi V1. What is phi V1? Remember, this is A11 W1 plus A21 W2 plus dot 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 AM1 WM. Yeah, where is it? Yeah, that's it. Following this, similarly, plus we'll have alpha 2 A12 W1 plus A22 W2 plus dot 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 AM2 WM. This continues, plus we'll have alpha n A1n W1 plus A2n W2 plus dot 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 AMN WM. Okay, now this doesn't look like a standard linear combination, because standard linear combination would be linear combination in terms of the basis vectors. So we club these things together in the sense that we bring all W1s together, all W2s together, all W3s together, so on up to all WNs, right? So then in that linear combination, if I look at the coefficients, those coefficients stacked up as a column will be phi V's representation in terms of BW, right? So let's try and do that. That would be, so I am going to club all the W1s together. This is one, so on, this is one. So if I club them together, what do I get? I get A11 alpha 1 plus A12 alpha 2 plus dot 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 A1n alpha n. This multiplying W1 plus A, now W2s, these are the W2s. So I have A21 alpha 1 plus A22 alpha 2 plus dot 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 up to A2n alpha n W2. plus, this will continue, finally plus A, this one, and so on, this one. A M1 alpha 1 plus A M2 alpha 2 plus dot 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 A Mn alpha n Wm, right? These are the coefficients. These are uniquely obtained because it's a basis. Yeah, BW is a basis. So therefore, this is equivalent to saying phi V's representation in the BW basis must be, first entry would be A11 alpha 1 plus dot 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 up to A1n alpha n, this one. Second entry would be the second coefficient, which is this one, so on. Finally, the mth coefficient would be AM1 alpha 1 plus dot 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 plus AMN alpha n, this one. This is the representation, right? But now notice that this is nothing but, from matrix vector multiplication business, this is nothing but, sorry, this is nothing but, define the matrix A11, A12, dot 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 up to A1n, A21, A22, dot 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 up to A2n, so on, AM1, AM2, AMN. This is the M cross N matrix. This multiplies alpha 1 dot 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 up to alpha n. Yeah, define this to be my matrix A, and note that this is nothing but V's representation in BV. What we get is phi V BW is the same as A V BV. That's it. That is what we wanted to obtain. Yeah, but now look at A. First column of A, A11, A21 up to AM1. What was that? Phi V1 represented in BW. Second column, A12, A22, AM2. A1, A12, A22, AM2. This one. And so on. The nth column, A1N, A2N, AMN. That is this one. So once again, what we obtain is that here, the A that you get is nothing but phi V1. Look at the first basis vector. Make phi act on it. Find out its representation under W, under the basis in W. Yeah, write it as a column. Then look at phi's action on V2 represented in BW. Yeah, get the column. Keep on doing this till make phi act on the nth basis vector of B. Yeah, represent that in BW. This gives you n columns. Each column is of length m, so you get an m cross n matrix. This is the matrix representation of phi, just like before. Right? This gives you a direct way of doing it. Right? Now for this module, so this is an end. So we put an end to this module, but we don't have any immediate attention problem for this module. Instead, what you will do is you will look at the older immediate attention problems in this new light. Yeah, and you'll solve IA1 and IA2 using what you just have learned here. Okay, that's the deal. Now, once you're done with that, please come back to module number 3. What we do in module number 3. So now I want you to pay very close attention to this particular fact. What I'm trying to say here is that, you see, So you see, this matrix representation of the linear map phi dependent crucially on the basis that we have chosen for V as well as for W, right? But now suppose I choose a different basis. Nobody stops me from doing that, right? So I choose a different basis for V as well as perhaps a different basis for W. That will give me a different matrix once again. So for the same linear map phi, I may have different matrix representations. That's a little kind of unsettling, right? It's discomforting because it's the same map, but two different matrices. How is that even possible? Yeah, even if it is possible, shouldn't there be some relation between these two matrix representations because of the fact that they actually are coming from the same linear map? Yeah, that is what we're going to explore in the next module. Okay, so till then, bye bye.